The number of signals in NMR are equal to the sets of chemically equivalent protons. Chemically equivalent protons are the hydrogen present in the same chemical environment. Each set of chemically equivalent proton give rise to a signal. To get the number of signals in the following molecules, first you have to identify the sets of chemically equivalent protons. In this molecule, there are 3 sets of chemically equivalent protons. Because these hydrogens are bonded to alpha carbon, and these 2 hydrogens are bonded to beta carbon, and these 3 hydrogens are bonded to gamma carbon. As they all 3 are in different chemical environment, there are 3 sets of chemically equivalent proton. So they give rise to 3 signals. Now let's examine second molecule. Here there are 2 sets of chemically equivalent proton. As these 2 methyl carbons are in the same chemical environment, they both are at beta position, and this proton is different from these methyl hydrogens because it is at alpha position. So this molecule will give 2 signals. Now come to the third molecule. Here there are 4 methyl groups, but these 3 are chemically equivalent. So they will give 1 signal, and this methyl will give another signal. So this molecule will give 2 signals. Let's practice a few more examples. In this molecule, there are 2 sets of chemically equivalent proton. So it will give 2 signals in NMR. In this molecule, there are 2 sets of chemically equivalent proton. As these 2 hydrogens are vinylic hydrogens, and these methyl hydrogens are at allylic position. So they will give another signal. So this molecule will give 2 signals. Now come to the next molecule. In this molecule, there are 3 hydrogens, and all 3 are chemically non-equivalent. As this hydrogen is bonded to the carbon which is directly bonded to bromine, so it will give 1 signal. This hydrogen is trans to bromine, so it will give another signal. And this hydrogen is cis to bromine, so it will give another signal. So that's why this molecule will give 3 signals. In benzene, all the hydrogens are chemically equivalent, so it will give just 1 signal. In nitrobenzene, these 2 hydrogens are ortho to nitro group. So it will give 1 set of signal, and these 2 hydrogens are meta to nitro group. So it will give another set of signal, and this hydrogen is para to nitro. So it will give another signal. That's why this molecule will give 3 signals. Now come to this molecule. In this molecule there are 3 sets of chemically equivalent proton. This hydrogen is bonded to carbon which is directly bonded to bromine. So it will give 1 signal. This hydrogen is trans to bromine, so it will give another signal. These methyl hydrogens are at allylic position, so it will give another set of signal. So that's why this molecule will give 3 signals. Now let's examine few more molecules. In this molecule, there are 2 sets of chemically equivalent proton. As the methyl hydrogens are chemically equivalent to each other, it will give 1 signal. And these 4 hydrogens are in the same chemical environment, so they will give another set of signal. That's why this molecule will give 2 signals. In this molecule, to get the chemically equivalent proton, first write down the relative position of hydrogen with respect to both bromine substituents. This hydrogen is ortho to this bromine and ortho to another bromine. This hydrogen is ortho to one bromine and para to another bromine. This hydrogen meta to this bromine and meta to another bromine. And this hydrogen is ortho and para with respect to both the bromines. So there are 3 sets of chemically equivalent protons. As there are 3 sets, this molecule will give 3 signals. Now let's examine the another molecule. Here there are 3 sets of chemically equivalent protons. These 4 protons are chemically equivalent. And these 2 protons are again chemically equivalent to each other. And these 2 protons are again chemically equivalent. So this molecule will give 3 signals. Now you will be able to calculate the number of signals given by any organic molecule. But how do we characterize NMR signals? In NMR, the frequency of radiation caused to flip a proton depends on the strength of magnetic field. Unlike to IR spectroscopy, where there is fixed wave number for each functional group. Energy difference between alpha and beta spin state is also directly proportional to the applied magnetic field strength. That means frequency of a particular proton doesn't have a fixed value. It varies on varying the strength of magnetic field and operating frequency of that instrument. That's why it requires a reference compound, and the signals of different protons are measured with respect to the signals obtained for the reference compound. Tetramethylsilane is used as a standard for proton NMR. It is used by dissolving it in deuterated chloroform. As deuterium is NMR inactive nuclei, it doesn't give any signal. And all the protons of tetramethylsilane are chemically equivalent, so they will give just one signal. And all these methyl protons are present in electron-dense environment, as the silicon is less electronegative than carbon. That's why all the methyl protons are most shielded among other organic molecules. As the methyl protons of TMS are the most shielded one, their signal occur at lower frequency. That's why the TMS signal are used to define zero position on the NMR scale. The signal of other protons are measured by calculating the distance from TMS signal. But as you know, the field strength and resonance frequency are directly proportional. So on increasing the magnetic field strength, the distance of observed peak from the TMS also increases. That's why it requires a scale that is independent to the magnetic field strength. Chemical shift is field independent number. It can be calculated by the distance from TMS in Hertz divided by operating frequency of the spectrometer in megahertz. So Hertz and Hertz will get cancelled out, and in the denominator 10⁶ will remain. That's why the unit of chemical shift is ppm, part per million. And the chemical shift is a measure of how far the signal is from the reference TMS signal. Most common scale for TMS signal is the delta scale. In NMR spectrum, TMS signal is used to define zero position on delta scale. Chemical shift of most of the protons fall in the range from 0 to 10 ppm on delta scale. How does shielding and deshielding affect the signals in NMR? For example, in this molecule, first identify the chemically equivalent protons to get the number of signals. So there are 3 sets of chemically equivalent protons. So this molecule will give 3 signals in NMR spectrum. But which peak belong to which signal? A set of protons are near to electron withdrawing nitro group. That's why these protons are deshielded one, as they experience higher B effective. Due to higher B effective, the energy difference between their alpha and beta spin state will be high. That's why they require higher frequency to flip their spin. That's why their signals occur at higher delta value. Such signals are called as downfield signals. So the signal observed at higher delta value corresponds to proton A. And C set of protons are present far away from the electron withdrawing nitro group. So these protons are the shielded one, as they experience less B effective. Due to lesser B effective, there is a small energy difference between their alpha and beta spin state. So they will require lesser frequency to flip their spin. That's why their signal occur at lower delta value. Such signals are called as upfield signals. So in this spectrum, signal closer to TMS or at lower delta value corresponds to C set of protons. And the signal obtained between A and C proton corresponds to B, because it is intermediate between A and C set of protons. Here there is characteristics value of chemical shift of few functional groups. When you closely observe the chemical shift for the corresponding functional group, you will see aldehyde, carboxylic acid, benzene and vinylic. They have exceptionally higher value of chemical shift. It is due to diamagnetic anisotropy. We are going to discuss it later. For methine proton, you will get higher chemical shift as compared to methylene protons, and methyl protons will have lowest chemical shift. Let's discuss it first, then we will discuss diamagnetic anisotropy. Methine protons are the protons bonded to sp3 hybridized carbon, which is bonded to just one hydrogen. For example here, this carbon is sp3 hybridized and it is bonded to just one hydrogen. So this hydrogen is called as methine hydrogen. Methylene hydrogen is the hydrogen bonded to sp3 hybridized carbon, which is bonded to 2 hydrogen. For example, here, this carbon is sp3 hybridized carbon and which is bonded to 2 hydrogen. So these 2 hydrogens are called as methylene hydrogens. And methyl hydrogen is the hydrogen bonded to sp3 hybridized carbon, which is bonded to other 3 hydrogens. Here, this carbon is sp3 hybridized carbon and it is bonded to 3 hydrogens. So these 3 hydrogens are called as methyl hydrogen. In NMR, chemical shift for methyl hydrogen is approximately 0.9 ppm, while for methylene hydrogen its value is 1.3 ppm and for methine hydrogen its value is 1.4 ppm. Similar chemical environment, the signal occur for methyl proton is at lower frequency than that of methylene and methine proton. For example, in this molecule, first identify the chemically equivalent protons in this molecule. There are 3 sets of chemically equivalent protons. These are the methyl proton and these are the methylene proton. They both have same chemical environment as they both are at alpha to this carbonyl group. So when you observe the NMR spectrum for this molecule, in the spectrum you will observe the signal for the methyl proton occur at lower delta value as compared to the signal occur for the methylene proton, though they have same chemical environment. Now come to the diamagnetic anisotropy. Anisotropy is derived from the Greek word anisotropic, that means different in different direction. Diamagnetic anisotropy means different magnetic field at different point. In such condition, shielding and deshielding depends on the orientation of molecule with respect to applied magnetic field. The prime example of diamagnetic anisotropy is the benzene. In benzene, there are electron clouds above and below to the ring. In presence of applied magnetic field, pi electrons of benzene ring start moving in circular direction, due to which magnetic field is induced in this way. When you observe the direction of induced magnetic field inside and outside the benzene ring, you will observe outside the benzene ring, the induced magnetic field lines are in the same direction as the applied magnetic field. So the protons present outside the benzene ring will experience more magnetic field as both the field lines are in the same direction. Such protons will be deshielded protons. But the protons present inside the benzene ring, they will experience less magnetic field as the induced magnetic field and the applied magnetic field both are in the opposite direction. Such protons will be shielded one as they experience lesser magnetic field. Let's try to understand diamagnetic anisotropy with an example of anulene. In the anulene, there are 2 types of proton, one which are present outside the ring and one which are present inside the ring. Anulene is similar to benzene as they both are aromatic compounds. And as we just have discussed, protons present inside the benzene ring experience lesser magnetic field as the induced and applied magnetic field are in the opposite direction. So similarly, protons present inside the anulene will also experience lesser magnetic field. So such protons are the shielded protons and their signal will occur at lower delta value. It is almost equal to 2.8 ppm. And the protons present outside the benzene ring experience larger magnetic field as the induced and applied magnetic field are in the same direction. Similarly, protons present outside the anulene experience more magnetic field and these protons will be deshielded one. And their signal occur at larger delta value. Its approximate value is 9.2 ppm. Another example of diamagnetic anisotropy is vinyl. In vinyl, there is pi electron cloud and in presence of applied magnetic field, pi electrons start moving in the circular direction and they induce magnetic field lines in this direction. This diamagnetic anisotropy is responsible for the unusually higher chemical shift of vinylic proton. Hydrogen bonded to terminal sp2 hybridized carbon has lower chemical shift than that of internal one. For example, in this molecule, this proton is bonded to internal sp2 hybridized carbon and its signal occur at 5.3 ppm delta value, while the proton bonded to terminal sp2 hybridized carbon occur at lower delta value than this and it occur at 4.7 ppm.